Okay.
Why we get started?
Yeah. Okay.
Today, it's a great pleasure to have Professor Lexing Ying for today's QPOM talk. So, as you probably know, Lexing is actually the professor of mathematics here at Stanford. So, since he joined Stanford in 2012, like almost 10 years ago, he has been pioneering a number of research fields in mathematics, in particular, in the areas of applied and computational mathematics, including the development of lots of interesting something algorithms. Yeah, I believe that's the main topic for today. And since he's local, so for those who are interested in chatting with Lexing, feel free to reach out to him after the talk so that you can have some follow-up. Okay, without further ado, so
well, thank you very much for the nice introduction. It's my great pleasure to give a talk about something I don't know too much about. I mean, the quantum algorithm. So I'm a student of mathematician, and I mostly been doing classical things, but somehow I got interested in quantum algorithms about 3 or 4 years ago during the COVID, and then ever since I've been spent a reasonable chunk of my time developing quantum algorithms.
you're saying some people got into making bread during COVID? Got into quantum algorithm?
I'm not sure which one is better. Yeah, I mean, I learned a lot from interacting with the physics colleagues here. So today I'm going to talk about the title is Harmonic Analysis for Quantum Algorithm. So what I'm going to try to share with you is how tools for harmonic analysis can help improving and accelerating the design of quantum algorithms. So first I would like to mention that these are the graduates. Ying was my student who graduated about by now 2 years ago. Hong Kong is an ICME peer student working with quantum algorithms. Then Ling and Zhi and Ding, Richard Zhang, these are students from Berkeley in Ling's group at Berkeley, UC Berkeley and Berkeley Lab. And Raoul Sharper was a student here, the joint Ling's group at Berkeley. And finally, there's the last piece of work is the joint work with Anto and Andrew Charles. Okay, so I don't need to say too much about quantum algorithms, and I think most people here are familiar with quantum algorithms. Here is a short list of some of the important or well-known algorithms on the basis factorization, which developed by Shor, which is 30 years ago, which is still at this point is most surprising and most important quantum algorithms. And there's also global type search algorithm, Hamiltonian simulation, which is according to Feynman, which is probably maybe the and only most important, probably only, but certainly the most important application of quantum algorithm is identification. And in recent years, there's also a lot of developments on a topic called the quantum singular value and eigenvalue transformation, which sort of unify some of these topics. So now, what is harmonic analysis? So I'm sort of trained as an applied harmonic analysis analyst. So the harmonic analysis is essentially a bunch of techniques which use to decompose complicated functions into much simpler ones. Okay, so some of the examples here are Gaussian functions, right? So for example, if you work with statistics, you work with Gaussian functions all the time. A Fourier transform where we decompose a function into sinusoids. A Laplace transform where you decompose function into decaying exponential modes. And there's more advanced topics like wavelets, which also have a lot of application in processing and signal processing. And there's also nonlinear versions, which as you will see in this talk. So in this talk, which I'm going to talk about, as the title suggests, I'm going to talk about harmonic analysis tools for developing, or at least helping develop quantum algorithms. So I'll talk about 3 topics. The first one is the phase estimation. So here you will see that ideas such as randomization and Fourier transform, these very fundamental ideas can surprisingly help you to develop state-of-the-art robust phase estimation. Then I'm going to talk about quantum signal processing, where you can see a nonlinear version of Fourier transform and FFT, and some really old algorithm, 200 years old algorithm like Harmonic method can help you solve some of the questions people today on the signal processing. And finally, I will briefly about this topic called quantum eigenvalue transformation, where we see the Laplace transform that actually help you. Okay. Most of the things I say here about quantum are not new because these quantum problems has been developed in the past 20 years, or some are really quite recently in the past 10 years. And the harmonic analysis tools have been around forever, right? Some of the tools are 200 years old, some of them are only 60 years old. So, but my contribution here is really trying to connect the dots to show you that some of the existing harmonic analysis techniques can be used for quantum algorithms. So I think there's probably quite a bit more to do, and so maybe it's sort of introduction point to show this connection. Okay, so the first problem is quantum phase estimation, which is one of the working concepts of quantum algorithms. So here's the setup. So my slides are kind of boring because I'm from math department, but but I hope it's clear. So actually the Hamiltonian. So and I use psi j and lambda j for eigenpairs. So psi j are the eigenvectors, lambda j for eigenvalues. And we assume that we have access to this operator, unitary operator, e to the minus iht. Okay, so in some cases it's easy to implement, some cases not. How to implement this Hamiltonian evolution itself is a big industry, so I assume that it's given to me as a black box. Now, the question is that given one of the eigenvectors, okay, phi 1, what I want to do is I want to figure out what is corresponding eigenvector. That's the job. Okay. So there are two simple, well-known versions of algorithms of quantum phase estimation. One is typically people call textbook quantum phase estimation, which use a quantum Fourier transform. That is considered to be a fully fault-tolerant version because it requires quite a bit of selective bits, and also circuit is sort of complicated. There's also another version which is called Harmonic, which is much simpler circuit, which is the one that we're going to talk about. So here the circuit for Harmonic. So here the U stands for e to the minus IH, and this unitary operator. So the first Harmonic has two circuits which are very similar, which is shown here. Only that the second one here you insert an S dagger on the first. So now if you feed psi 1 into the circuits, into these two circuits, and you measure the outcome. In the first circuit, the probability of getting 0 due to this interference is equal to half of plus the real part of psi 1 this bracket. And if you apply feed the psi 1 into the second circuit, and the probability of getting 0 is actually equal to half of the measured part of that one. So since you can measure them, you can subtract the half and you can combine them together. So essentially, by feeding psi into these two circuits, what you can get is that you can get some noisy estimate of this quantity here, which is psi 1 e to the I h psi 1. And you can calculate what that is, and because psi 1 is the eigenvector, so this is just equal to e to the minus I lambda.
Sorry, just to be clear.
Yeah.
You have some of each of the Heisenberg and the others are Hamiltonian.
Absolutely, sorry. Yes.
It's actually a superposition of the two, and so like.
Yeah, I thought about it. I should have used a bigger square.
No, no.
Yeah. So this is the
Yeah,
Hamiltonian, this is a. So what essentially the punchline is that is that if you feed this eigenvector into these two circuits, and you will get a noisy estimate of each of the eigenvector 1, and then by taking the log, you'll be able to figure out the 1 power. Okay. Now this circuit itself is very simple, but on the other hand, it's not very efficient. It's not reaching something people call Heisenberg limit. The reason is because in order to get an accurate estimate, you have to repeat the circuit many times. And so therefore the total running time for this Hamiltonian simulation is roughly going to be on the order of 1 epsilon squared. So but nevertheless, it's a very simple power. It's a very simple circuit. Now the problem that we're interested in actually for the multiple phase estimation. So therefore, instead of having one mode, I have multiple modes. So here again, I assume that these are eigen modes that have access to e to the minus IHT. But now the input is not superposition, it's not just one single mode, it's a superposition of S different modes. So the summation of psi j with weight to Cj. Okay, and you're adding from j from 1 to S. Now here I'm also going to introduce this Pj to be the modulus of the Cj squared. It's actually corresponding to the energy contribution of quantum modes. Now given this wave function, what I want to do is I want to figure out what is eigenvalues lambda 1, lambda 2 of lambda S. And one key True that we're going to use it, that we're going to introduce this spectral density, which is denoted by F here, which F lambda is equal to the summation of the Pj delta functions F lambda. So yeah, it's clear that, I mean, if you want to know this eigenvalues, it's equivalent to sort of knowing the peaks of this spectral density. So it's a useful function for this. Now let's take a look at how we apply the Harmonic test to this input wave vector, and what do we get? By simple calculation, you will see that this is actually equal to the summation of the Pj of the exponential with space lambda jt and add it together. Now, but using this function, this density that we just introduced, this can actually be written as an integral of e to the minus lambda jt f lambda lambda. Okay, so this is just simply plugging this here, and you see that by the definition of the delta function. But this is in fact the Fourier transform of the signal, right? F and what we're talking. So what this essentially says that Harmonic test now what it gives me is that for any t time, if you run the Harmonic test with time h with time t, you will get a noisy estimates of the Fourier transform. Now, suppose you can estimate all of them, which is expensive, but suppose you have them, then all you have to do to recover f lambda is just do an inverse Fourier transform. And that will give you the signal you want. And by looking at the peak of this function, then you'll be able to know where the eigenvalue is. Okay. Also, there's no action. Now, so these are the three important formulas here. And now, so therefore, a naive approach is the following: is that suppose we only want to recover the accuracy, the eigenvalues up to accuracy like epsilon, then what we can do is that we can sort of truncate this integral for real line. So we only need to care about minus f over f. So this is really corresponding to the resolution we want to resolve. And then what you can do is you can put a grid on top of it. For every time t on the grid, you approximate this Fourier transform. And once you have all of them, you can just add that together to get the inverse Fourier transform, which approximates your spectral density. And then you identify the peak of the spectral density, and that will be the eigenvalue. Okay. Now, but this is also quite expensive. Part of the reason is because I have to estimate so many grid points, and each of the grid points I have to use quite a few number of repetitions in order to resolve it to good accuracy. So therefore, this algorithm itself is also way over the estimate. So the question that is it possible to improve that? Okay. Well, the improvement is actually quite simple, and this is from the following perspective. Recall that we only need to resolve spectral density up to this accuracy epsilon, right? So therefore, instead of working with f lambda, it's equivalent to come over with a Gaussian, which is we denote by g epsilon, where epsilon is the standard deviation. So it will smear my signal a little bit, but if I want only to identify the peak with accuracy epsilon, that's okay. I can just work with that. Now, by the relationship between the convolution and Fourier transform, we know that f convolved with g epsilon, this very peak of Gaussian, is given by this, is by f Fourier transform times g epsilon. But g is Gaussian, so g epsilon Fourier transform is also Gaussian. It's a Gaussian with the reciprocal standard deviation, so the Gaussian with no epsilon. So now you take the inverse Fourier transform of that, you see that if I want to identify this function, well, if I somehow can have the access to the Fourier transform of f hat multiplied by this wide Gaussian, I'll be okay. So the key idea here is to figure out that, hey, G itself is a Gaussian, so therefore I can treat it as a distribution. So therefore, if you allow me to actually sample T according to this wide Gaussian distribution, I can write the whole formula as expectation of T sample from this wide Gaussian of at B. Okay, that's a key formula. Now with this observation, we're in good shape. So all we have to do is that is use a grid to resolve all the T values. I only need to sample T because at the end I only care about the integral, right? So therefore, I only need to sample T1 all the way to Tm. M is the number to be decided from this very wide Gaussian. And for each of this Tk value, I perform Harmonic test to get a noisy approximation of it. And in fact, in this case, we don't need to really get very accurate because here we really care about the average. Okay, so on every sample, it could be a little bit off. And then once you have that, and I just approximate the integral with this empirical sum. When I add them to average them together, what I will get is I will get the convolution of my spectral density with this peak Gaussian. And once I have that, I just identify the peaks and I'm done. So I'm here being a little bit sloppy in terms of the different constants, but the punchline is that you only need the m is equal to log move epsilon sample, that would be sufficient. And each of the sample, because I'm sampling from this wide Gaussian, the standard deviation is equal to move epsilon. So therefore, the time tk is roughly on the order of move epsilon. So therefore, each Hadamard test only needs the simulation time to be on the order of move epsilon. So when you add these, multiply these things together, you get the total complexity is equal to move epsilon times log move epsilon. And so this is reaching the reach the Heisenberg limit with an extra log move epsilon. So as mathematicians, usually, I mean, most of the time we don't care about the log move epsilon. And I believe that most of the CS folks and also physicists don't care much about it either. So therefore we claim that this is the optimum. So this is the first story. So here, the really is this simple tool is extremely simple. Is that one is that using Gaussian convolution, second is that two-das sampling problem, and third is there's also a little bit of harmonic analysis signal processing techniques which involved, which I didn't, but that's kind of minor. So this is the first story. So the second story is something called any questions? Okay. So the second story is about it's called quantum singular value transformation. So it is something that has been developed about by now it's maybe 9 or 8 years ago, and it's a really very powerful. So the setup is the following: is that suppose we have a quantum circuit for an operator A. Okay. So this circuit itself, it could be, I mean, so because the circuit has to be unitary, but A itself not necessarily unitary, or you have to do something called blocking coding. So if you're not familiar with this terminology, that's okay. But essentially, you can think about I have a quantum circuit to implement A, which will be denoted by U in this figure. Now, but my goal is to what? My goal is that if someone give me a function, B could be a rather general function. There's some kind of parity constraints involved, but at this level, let's forget about it. Think about B is like a nice polynomial, but could be quite arbitrary. What we want to do is that we want to build a circuit which implements BA, okay, through the application of the circuit for A and some control rotation. So you want to interlace these application of A with rotations such that at the end you will be able to implement BA. Now, I mean, you might ask, what is this used for? I mean, it actually has a lot of applications because BA could be what? BA could be some protection operator into the ground state. Then this will allow you a way to prepare the ground state. It could be like exponential function. This will allow you to prepare thermal states. It could also be 1 over x function, then or polynomial approximation 1 over x, and this will allow you to solve linear systems. Okay. So therefore, this has a lot of applications. It's a very general framework to solve many. So some key reference here is Low and Chang, which you first developed it, which is hard. This paper is monumental paper, but it's a little bit hard for me to read as outside the physics community. A much easier paper for me to read is this paper by Gideon, Su, and also Noah and Ruby. And the whole technique to identify these control rotations, because really the problem is that going from D to these control rotations. And this whole topic is from the signal processing. Joe Wan has written a very nice paper which influenced me tremendously. And also there's at Berkeley, Livingston has made a lot of contributions. So now, in order to precisely describe quantum signal processing, it's a little bit technical. So what I'm going to do here is I'm going to try to do a more general version, but somehow mathematically it's easy to describe. This general version is called the generalized. It's very creative name, generalized signal processing. Okay, and it's developed by Motlach and Levy about 2 years ago. So here is that instead of having a generic arbitrary blocking for your A, what you assume that you only work with unitary matrices, and assume that you have access to this 2x2 block, which is U and I on the identity. So so essentially you have the 1 qubit to control whether you apply U or you apply. And the problem is to use these rotations, general rotation, which is specified by these circuits, parameterized by 2 parameters, psi and phi. And the goal is that if you give me a degree n polynomial, okay, P, what I want to do is I want to find a sequence of these rotation angles to drive these control rotations, such that if I interlate these rotations and also these basic building blocks, U and I, I'll be able to produce a 2x2 block matrix, where the top right block implements BU. So essentially, you go implement this circuit, and you just extract this top right block, and this would implement the BU that you want to implement. Okay. And this B itself could be a general function, which is a polynomial approximation, for example, with some projection operator or some solving linear system. Now, so hopefully this is already quite logical, but this is the simplest version that I can find. Okay. Surprisingly, the problem is trying to find these rotation angles on the previous slides. These psi and phi's are related to another topic which has been around in the harmonic analysis for quite a while. So this started from the work of Hoffman, which is a mathematician and also pure mathematician at Yale. And Terry Todd and Chris Thiel wrote a very nice review article, and now I think it became a book on this topic. The original motivation for them is to study integrable systems. They're not working with SU2, they're working with SU1. But somehow the theory can be easily transferred into the SU2 setting. And there's a thesis by Tsai, which is a student, I believe it's either Tao or Jie, which really lay out the foundation of the things we're doing. Now, what is this nonlinear Fourier transform? I will explain the word nonlinear towards the end of the slides, but let me just tell you what that is. The problems actually look very similar to what we had on the previous slides. Is that given a polynomial P, which is a polynomial in the Z variable, and you introduce a complementary polynomial, which complementary Laurent polynomial A, which now is not polynomial Z, but it's a degree n polynomial will. Now, get from A, you can introduce something called A star. It's a bit technical. This formula is given here, but essentially what you do is that you take the coefficients of A and you take a complex conjugate of it, and whatever power of 1 over Z becomes power of Z. And these polynomials, they satisfy this condition. A star plus B star is equal to 1. Now, the problem with nonlinear Fourier transform is the following, is that given this matrix, which have these four functions, which I first specified here with this component relationship, this unitary relationship, I want to write this as a product of n plus 1 simple terms, where each of the term itself is driven by this coefficient gamma, okay? And I want to figure out what are these. So the problem is kind of similar. You give me a polynomial. Previously, I want to find the rotation angles, but here I want to find these coefficients gamma case. Now, one question is why do I have this nonlinear Fourier transform? And it looks like you have complex variables, so it's sort of believed that it's Fourier transform, but why is it called nonlinear? The reason is because very simple, is because when gamma k is very small, you can actually take out the whole product. The multiplication becomes additions. So therefore, you will see that the BD is actually roughly equal to this, which is summation of gamma k zk. And if zk is on the circle, this is really good Fourier. That's why people are nonlinear. But the motivation is quite different. Now, following some early work by Lexing's law, and we actually explicitly prove, I mean, it's not that hard to prove, but once you realize what to do, it's very easy. All the proof is here. But what we show that these two problems are equivalent. So if you want to work on this generalized QSP problem and finding these rotation angles, psi k and phi k, it's the same as finding these gamma k coefficients for solving this nonlinear Fourier. Okay? So here's the proof. The proof is very simple. Now I proved the one way, but it's really that we can go different ways. So suppose we solve the nonlinear transform, which means that this matrix on the left hand side is written as a product here. Now, because I only care about the VZ term, so therefore what I can do is I can multiply this polynomial matrix Zn and 1 here on the right hand side. That would change the first column, but it will not do anything to the second column. So therefore VZ will remain. So I'm dropping this 1 over square root of 1 over gamma k squared term because these are constants, and as long as I know things are going to be unitary, I can just put them at the end. So that's not worry about. Now, so therefore, this is the product I need to work out. But you can see that if you multiply them, what you can do is that you can, at every time, you can pull out 1 over Z diagonal Z1. Okay? So this is a very simple algebra. You just multiply, and then at the end, this is the identity. But now, if you take a look at this here, by choosing this psi k and phi k, which is equal to arctangent of modulus gamma k and r dot, okay, this matrix exactly become matrices that appear in this generalized case. And also this matrix Z1 here, if I lift them into the operators, that's exactly what we do. So that tells you that by solving this nonlinear Fourier transform problem, you can solve this generalized quantum signal processing.
I have
Yes.
quick clarifying questions.
Yes.
So when you show this kind of circuit diagram where control U gate is interlinked with this parameterized equations
Yes.
out here.
Yeah.
So am I always guaranteed to have this A, B minus B and A star form?
Yeah. If you do that, you will guarantee to have this form. Yes. Absolutely. Yeah.
That's why in the end, you do see this plug encoded.
Yeah.
Nonlinear transformation in off diagonal.
Yeah.
That's why you want to program that.
You can make it off diagonal by actually doing this sketch out there. Yes. Now, so therefore, the theorem tells us that in order to yes.
So, good question. So, does that mean for any B, I can find an A?
Not for any B, any polynomial.
For any polynomial, you can find an A with
That's
polynomial bound.
that's his size. Okay. So now, when I talk about generalized quantum signal processing, I will give you B, right? So, but in the non-uniform Fourier transform, non-linear Fourier transform, I have also this A as well. So the first question is that if I'm a quantum person who develop quantum algorithm, I should take the B that you give me and develop A and A star, and then from A star B to find out these numbers. Okay. So these are the two computational tasks. So previously the theoretical theorem, but now we are put on the engineer hands of the engineers and we try to solve these two engineering problems. Now, the first problem is that given B, how do you find A and A star? So recall A is a polynomial with Z, and A star is a polynomial with Z. So there are many choices for A, which can work. But in fact, for numerical stability reasons, which is quite technical, but I cannot, but the really the idea is that there's one A star, which is the best for numerical stability reasons. The reason is because these polynomials can be very high degrees, thousands or tens of thousands, even hundreds of thousands of degrees. You want to approximate, for example, projection into the ground state. It's very peak, so you have to very high level polynomials to approximate. So in order to compute all these phase factors accurately, we need this A star to be the so-called outer function. So what is the outer function? The outer function is really the polynomial such that all the roots are somehow outside the unit circle. There's nothing inside the unit circle. So in fact, for every one outside roots outside the unit circle, there's one inside the unit circle. You can actually choose which one you like to make into your A star. You can choose the one outside or inside. And in fact, both will work theoretical level. But in order to have the numerical stability, you have to choose the roots. And the second more technical thing is that so you heard I mentioned about roots. So what would you find this A star? So let me just find all these roots outside the unit circle and then multiply them together. Then I will give you the polynomial. But unfortunately, from the numerical linear algebra perspective and numerical approximation perspective, finding the roots is not a very stable process. So therefore, we want to bypass it. We don't want to find the roots. We want to find the coefficients of these polynomials directly. Because when we compute the phase factors, as we will show you, you only need the representation of these polynomial coefficients rather than the roots. So this part gets a bit technical, but I just want to give you a feeling of this. There's two solutions. The first solution is appeared quite recently in this paper. It's used an old algorithm called the Wise algorithm, which is 60 years old. So for those of you familiar with complex analysis, there's something called the Blaschke decomposition, which essentially take a function which try to decompose it into simple factors along with the function which has no zeros unit disk, and the Wise algorithm developed for that. And these gentlemen figure out that these authors try to figure out that you can actually use the Wise algorithm for exactly the same purpose. So here I'm not going to the detail to explain why, and just showing a picture to pretend that I tell you all the details. But I just want to show you that the algorithm is extremely easy. So all you have to do is just take the b function square, take the square root 1 minus, take the square root, and take the log. That gives you some function called r. And then there's another edge here. This is not Heisenberg, this is not Hamiltonian, but this is Hilbert transform. So if you take this r function and you take the minus I of the Hilbert transform and you plus and minus, you get this g and g star function. And somehow magically you take the exponential of g and g star, you will get back these two polynomials. So there's some deep relationships going on, but so this is extremely simple, very easy to code up, and then numerically computing Hilbert transform on unit circle is also very accurate. Now you may ask the question, why do we have to go to transcendental functions that be not exponential? Because everything should be remaining polynomial. Well, if you want to work with polynomial rational functions, there's also another way which you use something called a pruning step. So again, this requires a bit of time to explain this. So what I decided to do is just to tell you the main idea. So the idea is the following: that instead of working with the log of 1 over 1 minus b squared, so when you work with 1 over. So what you do here is that you turn the roots that you want to find into the poles. So then the job is that you want to isolate the poles inside the unit circle and the poles outside the unit circle. How do you do that? Well, you can do that by contour integration. Because by contour integration, you know that if you draw a contour here in the unit circle, you do contour integrations, you're going to get the moments of all the poles inside, but not the poles. So therefore, by doing contour integration with different factors, you'll be able to get the different moments of the poles inside this. Once you have the moments, there's this technique called the prudence methods, essentially allow you to recover the spice of a certain distribution from its moments. And this will involve computing the negative coefficient of Fourier transforms and assemble this into a Toeplitz matrix and find out the null space of the Toeplitz matrix. And these coefficients will actually give you the coefficients of this polynomial. It's a complicated story, but the punchline I want to say is that these things all can be computed numerically in a very stable way. This involves only contour integrals, resolving quadrature. Fourier transform, you can do this fast Fourier transform, it's also very stable. And the finding null space can be done with the numerical implementation of single value condition, that's also. And this prudence method, which is really 200 years old, and is known for not being stable under noise. But in this setting, it's perfect because there's no noise at all. Someone give me B, and I can compute the GZ perfectly, and I can do quadrature with exponential accuracy perfectly. So the noise is not a problem. So that's why prudence method is perfectly for this.
So just to clarify, there's a small n to the small n to b. So
oh, sorry, this is a mistake. This should be n. These are the coefficients of this. Sorry, we reuse the formula in our previous earlier talk, which is for QSP. So in QSP, you have 2D, but here 2D is n.
Is it guaranteed to have the outer coefficient using this?
Yeah.
And then also the previous method.
Previous method is also guaranteed. Now, second pass, which I mentioned, the two passes. The first is go from B to A, and the second pass is going from A, B, and to the gamma case. And the relationship is really just given by that. Now, the standard algorithm to implement this is called layer stripping. So the idea is, to fully explain it, we need to write a lot of formula. But the idea is very simple. Because these are degree n polynomials. They involve n plus 1 coefficients. So the idea is that hopefully I can take out the first coefficients, figure out what a gamma 0 is. And once I figure out a gamma 0, somehow I can take the inverse of the gamma 0 term and multiply on the left hand side to reduce the left hand side in terms of instead of the degree n polynomial, but to degree n minus 1 polynomial. So I reduce the problem to 1 degree less. Right? And then if I keep doing that, I'll spit out these gamma rotation angles 1 by 1, and at the end I will shrink this vector on these polynomials to degree 0, then I'm done. Now, what is the complexity? What is the cost of this? Every step which you need to do is first, obviously, you have n steps because you have n coefficients to spit out. So then, every time what you're going to do is you're going to take the inverse of this time 2 by 2 matrix and multiply here at the left hand side, and then multiply with these two polynomials. Right? So to work with polynomial, you need to work with the coefficients. So therefore, linear combination of the polynomials only correspond to linear combination of the coefficients. So therefore, the cost of the implement every step is also only. So the algorithm has a cost which is n times n, which is which is not a big deal if you work with n small, but if you want to work with n, which is like tens of thousands or even millions, hundreds of thousands, for example, and this becomes quite expensive. I want to say that this is not bottleneck, but we have a. It's okay if you're willing to wait for a few minutes on your laptop, that's fine. But the interesting thing is that harmonic analysis and ideas from fast Fourier transform also allow you to accelerate this. So the idea is also very simple. So this is also a fast algorithm proposing this paper, which I just mentioned earlier. So the idea is that instead of working on trying to figure out all the coefficients together, let's try to cut in half and try to figure out the top part and bottom. The key realization is the understanding is that if you look at the top part, okay, let's forget about how it's computed. But conceptually, it's only depend on the first half of the coefficients of my A and B matrices, A and B polynomials. So they only depend on the top of my A, B coefficients. Okay. Now suppose that it can be computed. And then what we can do is that we can actually do a group diversion of the layer stripping by stripping out all of them together and then update the second part of the coefficients. Okay. And now, well, it turns out that this also involves the polynomial multiplications, and it can be accelerated by using fast Fourier transform. We all know that polynomial multiplication essentially is a convolution, so it can be accelerated by fast Fourier transform. So therefore, if you group that all together, the whole group is layer stripping operation for all n minus 1 or sorry, n over 2 coefficients only takes cost of n log n. So what we have done is that we decompose the original problem into two subproblems. We do this one first, and then we do a fast Fourier transform, accelerate the computation, and then do the later part. Now you can ask the question, how do we do this part? We use two origin parts, which half of the size. It is very simple, you just recursion, because everything is self-similar. So the whole complexity is analysis is given by this line. And so for those of you who have taken like a complexity algorithm classes, when we talk about sorting, right? This is the complexity that we get by this recursion sorting, right? The only difference is that sorting here is n, but here because we transform, so it's n log n. But the estimate is very similar. At the end, it's implied that the total complexity is only n log squared. Okay, so this is also linear. All right, so this is the second story. So what is the idea here? The idea is that some older techniques, including Fourier transform, fast Fourier transform, nonlinear Fourier transform, Wise algorithm, Pruni's algorithm, and somehow can be used to give you a very robust and efficient way to compute all these phase factors that people need in quantum signal processing and generalized quantum signal processing. So the last story is about quantum eigenvalue. So I want to emphasize there's a difference between quantum eigenvalue transformation and singular value transformation. Well, quantum singular value transformation, typically you're working with permission matrices, or you work with general matrices, but you want to compute the singular value coefficient. The singular value coefficient are good because the first factor and the last factor you get by singular value coefficient are unique. So this gives you the stability error. Okay. Eigenvalue transformation is different. Especially, we want to work with general operator A. So it's not permission, it's not unitary, it's not normal, it's a general matrix. So therefore, if you do eigenvalue decomposition, you know that the eigenvector matrix is going to be, you have no control over its form, right? So that's why it's a different problem. But nevertheless, we want to do something similar. In that given this operator, general operator A, what I want to do is that for any general function, well, I will put some constraints on it, but besides these constraints, it could be quite general. Give me a general function h, I want to build a circuit which implements ha. So here we're going to restrict ourselves working with ha, which should be bounded and also impose some constraints. So for the matrix A, so essentially what you want is that you want to make sure that the ha itself to be bounded on the spectrum of A. So we assume that A can be decomposed into some of the two matrices. So this is the permission part, this is the anti-permission part. So because I had an I here, so we can assume that an L and H holds permission. So I also require this L to be bigger than or equal to 0, meaning that's positive definite. So essentially this line says that I want to restrict myself to work with A's such that its spectrum, its eigenvalues are located on the right half. And accordingly, I want this function h to work with also be bounded on the right half plane. And also something provide, as you will see, that it's also useful to assume that it's analytic, but also to be analytic. So these are the conditions I want for this h function. It's on the right hand side, half plane, it's analytic, bounded, and k-analytic. So now let's assume let's consider the simplest example of such a function. HA is equal to e to the minus. Right, this is the exponential function on the right half plane. It's e to the minus c is essentially equal to 0 as analytic. So one thing I didn't mention is that we also want to try to implement this using something called Hamiltonian simulation. The reason is because Hamiltonian simulation is really become sort of like the robust technology, and we want to implement something as the Hamiltonian simulation is a subroutine where you have most robust algorithms. So the question is that can we implement Hamiltonian simulation for this function? Well, A, as we know, it has two parts, the L plus IH. Let's just take on the L part. And in fact, if you only care about e to the minus L, then this contour integral formula, which allows you to write e to the minus L as a bunch of e to the minus I L. What is this coefficient contour this time? And this is not hard to prove. The reason is this simple contour integral and you realize that the only point you have for this function is that k to the minus I, and like e to the minus I is exactly. Now, what if you don't have just L, but you have L and plus H? I want to add that together. So in this nice paper by Dong An and Jin-Pen Liu and Ying, they show that in fact this whole formula works, and they show in a slightly different formula, but this is a simplified version. And the reason is because if you take a look at I L plus I H, this eigenvalue is also on the right hand plane. So therefore, for every eigenvalue this works, condition. But unfortunately, this formula is not very friendly to competition, and part of the reason is because you see that you have 1 over this k, decay like 1 over k. So therefore, its decay is extremely slow. So in fact, this formula is only makes sense since this whole value sense. Okay. In fact, what you can show is that by N, Charles and Ling and another paper where they showed that instead of using this, in fact, it's just using this function, using the function which equal to 1 here. You can replace it with any function fk, such that f minus I at the minus I which is 1, and you're in the lower half plane, and then you keep a large values. This whole formula is proofs. Again, the proof is by using contour integral. But the advantage of this is that as long as fk decay very rapidly, for example, you choose this function, then this integrand itself is actually decay very rapidly. So therefore, for numerical quadrature numerical equation, you only need to worry about the small value. So this whole is a story for e to the minus, right? This is one special function, which is very useful, but nevertheless, it's one single function. What about this function hk? Okay. What if I care about the general function, which is analytic from the right half plane and also decaying? Can we do anything? Again, here is another piece of harmonic analysis coming to help us is Laplace transform. It could be shown that under these conditions and in some other minor technical conditions, such a function can be written using a Laplace transform into a linear combination of these modes, e to the minus at. Previously, I only have e to the minus a, but now because I have to update it, so I have t factor here, but whatever formula I have on the previous slides also added here. And this L hat function, and in the sufficiently reasonable conditions, it can be shown on the L. And you can also assume that it's a function, so therefore you can do it. Now, once you have this formula, we can combine with the formula that we have developed, we have seen on the previous slide, which decompose e to the minus a into Hamiltonian variables. So all we have to do is just take this formula plug back in here. And the first thing to grow is over this parameter of the Laplace transform, and the second is involve this k factor, which comes from the contour integral. Now the algorithm now is very simple. So all we need to do is just do numerical quadratics. Okay, you have to be a little bit careful to how to discretize accurately, but for example, using trapezoid rule will work. It might not give you the optimal one, but you know. So all you have to do is discretize this t integral with quadrature quantity a, and also the k integral with quadrature b. And then you just approximate this double integral with a double sum with corresponding weight, then you will get a good accuracy, very accurate approximation of this HA function that you want. Now, if you want to implement a quantum circuit, all you have to do is that for each of these exponential terms, you implement the Hamiltonian installation, and then you do the else linear coefficient. All right, so let's do a short summary. So in this talk, I talk about three things. One is phase estimation, quantum signal processing, the last is quantum estimation. So each of them are quite important building blocks or toolboxes in quantum algorithms. There are many things to talk about it. And I showed that in each of these cases, at least in the state-of-the-art implementations, harmonic analysis play an important role. So in the first case, it's very simple Fourier transform, very kernel. And the second one is nonlinear Fourier transform. It's a little bit advanced, but also dozens of years old. And very old algorithms like Bruni's algorithm, and the final one is again, as I said at the beginning of this talk, and I'm not introducing anything new here, I'm just trying to connect the dots. between these old harmonic analysis techniques and somehow these interesting new harmonic. And hopefully this will be a starting point for much longer.